Hi, this is Gary Rubenstein. This video is about how to solve quartic equations, and this is not something that most people know how to do using algebra. I've made two other videos about quadratics and cubics. If you're not sort of proficient in those two things, you probably want to watch those two videos first. Here we go. First, I want to remind you that this is a quadratic trinomial, but it's special because if you take the 6 and divide it by 2 and square it, you end up with 9, which is the constant term. When that happens, it's called a perfect square trinomial, and it can be factored like that. In general, we could say if b over 2 squared is equal, if b over 2 squared equals c, that will happen. That's if there's no coefficient there. Even more generally, if there was some coefficient aside 1, we can say that if b squared minus 4ac equals 0, that would happen also. Let's take a look. For this quadratic, if I calculate b squared minus 4ac, I get 6 squared minus 4 times 1 times 9, which does equal 0. So that's perfect square quadratic trinomial. But the first quartic thing I'm going to show you, it's going to be very similar. Notice it has coefficients 1, 6, 9, just like this first one did. This, if you have a quartic that's got no cubic term and no x term, it's basically like a quadratic, but instead of x, it's like x squared is the thing. It's sort of variable. So if you have a fourth degree equation like this, and you notice that b squared minus 4ac equals 0, in this case, 6 squared minus 4 times 1 times 9 does equal 0, then this thing can be factored. And the thing it factors to in this case is x squared plus 3 squared. This number is going to be half. That number is going to be b over 2. Now, most fourth degree equations have more have an x term in there, or maybe an x cubed term, but at least we have our first thing dealing with quartics. I want to say a little bit more about perfect square trinomials. Here's 4x squared plus 12x plus 9. If you do b squared minus 4ac, you get 12 squared minus 4 times 4 times 9, which is 144, minus 144, which is 0. So this thing is also a perfect square trinomial. And if it is, a sneaky trick for factoring it is basically if you take the square root of the a term, which is 2, you get 2x. And if you take the square root of the c term, you get 3. And if you multiply that out, you will end up with the 12 in the middle. You could even get something real strange looking, like 14x squared plus the square root of 3584x plus 64. Well, that's got an unusual coefficient there. But if I calculate out b squared minus 4ac, well, b squared is obviously 3584 minus 4 times 14 times 64. Well, that ends up being 3584 again. So even this thing's a perfect square trinomial. And that would mean that it would factor, if we know for sure it's a perfect square, you just take the square root of this and the square root of that. Now let's look at our first quartic equation. First quartic equation is one, it has no x cubed term, and it has no x term. And if you see something like this, there's a chance, this one's not a perfect square, but there's a chance that it factors. So I'm going to make a note. It's like the quadratic u squared minus 10u plus 9. Now that would factor to u minus 9u minus 1. So this thing factors to x squared minus 9, x squared minus 1 equals 0. And each of those pieces, if the product is 0, one of them is 0. So either this is true or x squared minus 1 equals 0. So one of those is true. So x squared equals 9 or x squared equals 1. So x, actually, there's 4 answers, plus minus 3. And those are the 4 answers to this equation. Now, most quartics aren't as easy as that. But we're going to build up. We have a few more before we get to the general. Here's the same question, but I want to remind you that another way to do this question is to do completing the square. So again, we have 3 terms, and the way you do completing the square, this is in the video for quadratics, we could subtract 9 from both sides. And then we say, well, in order for the left-hand side to be a perfect square, we could take minus 10 over 2 and square it and get 25. That's what would need to be there. But if you add it to the left side, in order to make the left side a perfect square, you have to add it to the right side also to make it still true. The left side factors to x squared minus 5 squared, and the right side turns into 16. Then we can continue this question, because if something squared is 16, it's either plus or minus 4. And then when you add 5 to both sides, x squared equals 5 plus or minus 4. That means x squared equals 9, or x squared equals 1, x equals plus minus 3, x equals plus or minus 1. I just wanted to remind you about the completing the square. Process of solving quadratics, because it's gonna be part of this lesson also. Okay, now for a pretty unusual looking equation. X to the 4th minus 10x equals x squared plus 6x minus 16. So I have here, this should be 10x squared. So let's just look at this. I know I could move it all over to one side, but I'm not going to. I like that this has an x to the 4th and an x squared, and this has an x squared, an x, and a constant. Now I want to do completing the square on this. And at the moment, this left side is not a perfect square. And actually the right side is not a perfect square either. Well, to make the left side a perfect square, I would calculate negative 10 over 2 squared equals 25. And I would add 25 to both sides. And if I combine the minus 16 and the 25, I get plus 9. Now this left side is a perfect square. This is x to the 4th, is a perfect square trinomial because we completed the square in order, so it definitely was going to become one. But something really lucky happened here, because this 9 that ended up here, if I take 6 over 2 and square it, I get 9. So the right side is a perfect square trinomial also. And that was really lucky that that happens. But if that does happen, let's just see how we would continue the question that's squared. Now, when both things are squared, I can kind of take the square root of both sides, but I have to be careful. I actually get two, it splits up into two different things. Just like if this were a number here, like a 9, and we'd say it's either +3 or -3, same idea here. I split it up, one with a plus, one with a minus. So this turns into x squared minus 5 equals x plus 3. And this one turns into x squared minus 5 equals minus x minus 3. Now those things are both quadratic equations, so I can bring everything over to one side. Now this right-hand side can factor to x plus 2, x minus 1 equals 0. And I get two answers, x equals minus 2 or x equals 1. This left-hand side, though, would require the quadratic formula. B squared is 1, 4ac is 32, so end up with that. And in case you're wondering, those two answers are about negative 2.37 and positive 3.37. Well, this was this equation here was very lucky. Actually, the equation started up here. It didn't have the 25 or this. It's pretty unlikely that when you complete the square on the left, that the thing on the right also becomes a perfect square, but I made that question, so that would happen. We'll see what happens when that doesn't happen. Okay, now let's look at another more involved equation. Okay, so here I have a Quartic equation. There's no x cubed term. That's called a depressed quartic, and I'm going to show you those first. One thing you could do is you could add x squared to both sides and add 6x to both sides. And also take away 16 from both sides. And you would end up with x to the 4th minus 10x squared is equal to x squared plus 6x minus 16. Well, that should look familiar because that was the exact equation that we had before with these four answers. So here was an equation, and again, we got lucky, but by adding x squared to both sides, I end up with an x squared here. And by adding 6x to both sides, I get this situation where I have an x to the 4th and an x squared, but no x term, because the x term is here. And maybe we get lucky that when we complete the square, by adding 25 to both sides, we end up with a perfect square trinomial with x to the 4th, x squared, and a perfect square trinomial with x squared and x. Again, very unlikely for that to happen, but we're going to see that it's possible to sort of force that to happen, and that's coming up. That's the big example that is about to happen. Let me see if So the equation I want to look at now is y to the 4th plus 6y squared minus 60y plus 36 equals 0. And this is the big instructional example here. It's a depressed quartic. I used y. You'll see why I'm using y later, but for now, let me show you what the process is. Now, I'm not going to add y squared to both sides like I did before. There's a better way. So step one, and this is the process. Step one, add 6y squared to both, add 6y squared and 60y to both sides, and also subtract 36 from both sides. Okay, what does that do? Well, the left side turns into y to the fourth plus 12y. These cancel out. And on the right-hand side, I have 6y squared plus 60y minus 36. Now, my goal is to somehow do something to both sides so that both sides become perfect square trinomials. So first attempt I'll do is since 12 over 2 squared equals 36, if I add 36 to both sides, I'll get y to the fourth plus 12y squared. This should be squared, and that should be squared also. Sorry about that. 6y squared plus 60y. These 36 cancel out. That was kind of lucky. That usually doesn't happen, but it doesn't change things that much. So what's happened here is that the left side is definitely going to be a perfect square trinomial now. But the right side is not a perfect square trinomial. So that's too bad, because if the right side was, we'd be able to go back to a situation like this, or like this. But it just didn't happen. The left side is a perfect square trinomial, but the right side is not. And it's really, this is the real clever insight, which is, what am I going to do now to both sides? Well, the trick is, this left side is a perfect square trinomial because it's y squared plus 6 squared. I'm going to introduce a new variable, which I'm going to call z. Now, no matter what z is, the left side is going to be a perfect square trinomial still. Because let's say z is 1. Then it would be y squared plus 7 squared, still a perfect square trinomial. But what's weird here, or what's difficult, is what am I going to do to the other? I can't just stick a z into the parentheses there. I have to balance that out by putting some stuff on the right-hand side, and I can't just put a plus z on the right-hand side because that z is part of a whole thing that changes the left side by a lot more than z. I'm going to have to add something. But what exactly? The way to see what to put on the right-hand side is to see what really happened. When I stick this plus z in, how much does it change the whole left-hand side by? So I want to compare y squared plus 6 squared versus y squared plus 6 plus z squared. And the way to do that is to rewrite y squared plus 6 plus z as y squared plus 6, and then the plus z there. Because now I can treat this as like one thing, and it becomes y squared plus 6 squared plus 2z y squared plus 6. That's what would happen if you took this thing. Why don't I show you that because this is the most difficult part of this. So if you do so-called FOIL, you get y squared plus 6 squared. Here is z times y squared plus 6, and here's another z times y squared plus 6. That's where the 2z y squared plus 6 come from. And the L is z times z, is z squared. So notice that y squared plus 6 plus z squared is this much bigger than y squared plus 6, without the z squared. So the thing I need to add to the other side, when I put the plus z here, I balance it out by putting a 2z parentheses y squared plus 6 plus z squared. That's what goes. And now my equation is looking pretty ugly. But the left side is still a perfect square trinomial. Now you might look at the right side and say, well, that's a big mess. Let me clean this up and write it again. So the left side is going to be a perfect square trinomial for any value of z. This right side, I can do some stuff with it, rearrange terms. Let me just rewrite it first, though. This is the sort of the hardest part of this process, so I just want to take my time through this. If I simplify the right-hand side and multiply, distribute this 2z through, I get 2zy squared plus 12z. That should be z squared. And now I just want you to notice that there's a y squared here and a y squared there, so I can combine those. By saying 2z plus 6y squared. Oh, I lost my y? When did I lose that? Let's bring them back. That's the only y term in this, so it's plus 60y. And the stuff that doesn't have y's in it, there's a z squared, and there's a plus 12z. Sometimes there's another number in there also. If this 36 didn't cancel out, there would have been also an extra number in there, but that doesn't make it really, it makes it a little bit harder, but the process would still be the same. Okay, so the left side is y squared plus 6 plus z squared. So the left side is a perfect square trinomial. The right side, well, it would depend what z is. Maybe, depending on what z is, the right side, no matter what z is, the left side is a perfect square trinomial. But the right side is only going to be a perfect square trinomial for certain values of z. Well, a perfect square trinomial happens when we want to force, I'm going to write this down, what z makes b squared minus 4ac equal to 0. So I'm going to come here and say, well, on the right-hand side, b squared is 60, so 60 squared minus 4 times a, which is 2z plus 6, times c, which is z squared plus 12z. I'm glad that 36 cancels out because it'd be a little harder with that. And I want to find the value of z that makes that equal to 0. So this becomes a brand new equation to solve on its own. That's just to figure out what the magic z value is, because no matter what z is, the left side is going to be a perfect square trinomial, but there's a perfect z that will make the right side a perfect square trinomial also. And if you take this equation, this one, and you work it out, 3600 minus 4, it's a little FOIL here, 2z times z squared is 2z cubed, 2z times 12z is 24z squared, 6 times z squared is 6z squared. I'll change this to a 30 then. And 6 times 12z is plus 72z. Distribute the minus 4 through, so it's minus 8z cubed minus 120 z squared. 72 times 4 is 288 z. I'll move everything over to the right hand side. 8z cubed plus 120 z squared plus 288z minus 3600. And then I'm going to divide everything through by 8. I might end up with some decimals. Eight into 288 is actually 36. And this becomes 450. So I have this new I have this new equation. Well, this equation is a cubic equation. And that's a cubic equation that we actually solved in the last video. Let's go back and see. So if you didn't watch the cubic equation video, you'll want to watch that, because then you'll know why that equation, here it is, it is a z now instead of an x. And what we did to do that equation, if you watch the cubic equation video, is we created a depressed cubic equation first, which ended up being this. And we solved it, and we got 9.0098. And that meant that the answer to this question was 4.0098. You can watch the video for cubics for that. And that will be the answer for z. So z is equal to approximately 4.0098. It's about 4. Again, there's a process there. You would first turn it into the depressed cubic, w cubed equals 39. I'm running out of letters. 39w plus 380. Using the transformation of z is equal to w minus 5. W became 9.0098, and that made z is equal to w minus 5 is equal to 4.0098. Anyway, that's to watch the previous video. All that work was to get the value of z. And now that I know the value of z, I could plug it in into all the occurrences of z. And this equation, this one, turns into y squared plus 6.0098 squared is equal to this 2z plus 6 is 14.0196 y squared plus 60y. And this z squared plus 12z is 64.196 approximately. Now the left side is definitely a perfect square trinomial. And if you take the right hand side and you do b squared minus 4ac, you wouldn't get exactly 0. B squared minus 4ac, I'll say is approximately 0. Because I did some rounding. You know, this 4.0098 was rounded, so that makes these two things rounded, but it would be really, really close. Now, to simplify things a bit, I'm going to say, you know, this process is going pretty well, but I'm going to accept having, like, I'm going to round right now. I mean, that 6.0098 is pretty close to 6. And this 14.0196. By rounding these numbers, this thing on the right is no longer a perfect square trinomial. It's not true. 60 squared minus 4 times 14 times 64. It's pretty close to 0. B squared minus 4 times 14 times 64. It's equal to 16. You know, it's considering, you know, this is a pretty big number, 3,600, but it's not 0 anymore, but it's still, like, close. If you really want to get a really accurate answer, you would not do any rounding. But the reason I'm doing the rounding is because, just for teaching the concept, this right side, assuming it was a perfect square trinomial, it would be square root of 14y plus 8 squared. Again, these are rounded, so everything's going to be off by a tiny bit now, but for teaching the concept, this is the idea. Remember I said before about if this is a perfect square trinomial, because b squared equals 4ac, the factoring would be whatever the square root of this is, would be the coefficient of the y, whatever the square root of that is would be the constant. Well, now I can take the square root of both sides. I get plus or minus square root of 14y plus 8. And that turns into two equations. Y squared plus 6 equals root 14y plus 8. Or y squared plus 6 equals negative root 14y minus 8. If I move everything over to one side, I get y squared minus root 14y minus 2 equals 0. And over here I'd get y squared plus root 14y plus 14 equals 0. So those are two quadratic equations. This right-hand side has no real solutions. But the left-hand side, if I use the quadratic formula, we would end up with two answers. Y is equal to about 3.1, and y is equal to about 0.65. And those are the two answers to this original equation. This one. All that work to get the solution to the depressed Quartic equation. Moving things over, adding in this z here, finding what z would have to be to make the right-hand side a perfect square, but that itself required doing a cubic equation, which turns into a depressed cubic to solve it, and then going through all this. And 3.1 and 0.65 are the two answers to that equation. Now, the final thing to tell you about in this video is, what if it's not a depressed quartic? What if the equation has an x cubed term? Well, in the last video I showed you that to make a full cubic that has all the terms into a depressed cubic, we replace x with y minus b over 3a. Well, a similar trick works for quartics. If I replace x with y minus b over 4a, which in this case is y minus 8 over 4 times 1, which is y minus 2. And if you replace each of the x's with y minus 2's, and you're really careful with your calculations, the equation y to the fourth plus 6y squared minus 60y plus 36 equals 0. Well, that should be familiar because that is the exact equation that we just did. So after all this work, we found two answers for y were 3.1 and 0.65. But remember, to solve for x, x was y minus 2. So that either equals 3.1 minus 2, which is 1.1, or x equals y minus 2 equals 0.65 minus 2, which is negative 1.35. And those are the two answers to this Quartic equation. This process was published in Ars Magna in 1545, and I think this is the exact example they used. Cardano gave credit to his student, whose name was Ferrari, for figuring this process out. But Cardano didn't think it was a very important process because he thought so geometrically and there was no such thing as a fourth dimensional object. Anyway, I hope you liked that video. It took me a long time to learn how to solve cubics and quartics. I had to read Ars Magna. It's not something that's taught in high school, and in college, I guess it might be taught sometimes, but I didn't learn it in college. So, as a math major. So there you go. Now you know how to do cubics and quartics. If you're looking to learn how to do fifth degree equations, well, there's not going to be a process like this. That was proved to be impossible. So now you are the master of the ones that are possible. Thank you.